for some integer k. That's just a definition of congruence, right? And then phi is p minus 1 times q minus 1. So now m hat is congruent to m to the k, some integer k, times p minus 1 times q minus 1 plus 1 modulo n.
I have a question.
Yep.
At the bottom of the slide above, where it says m hat equals c to the d,
Yeah.
don't we only know that m hat equals c to the d mod phi?
You are absolutely right. So thank you. That is, yeah, that's a very important mistake that I made. These are not equalities. These are congruences because m hat is in fact a remainder modulo n. So let's, yeah, that's actually very important. So let me correct that. But these are all congruences. Yeah, and this is good enough because anyway, the only way I was going to use it was that this is a congruence modulo n. Okay. So now I'm going to I'm gonna prove a claim. So by the way, what is this looking like? What does this expression now remind you of? Fermat's little theorem, right? It's something raised to the p minus 1. Now the only glitch is the thing that we're not doing things modulo prime, right? We're doing things modulo pq. Here. So now what we're going to do is we're actually going to prove is that we're going to prove a little, I guess, claim, which is sort of a generalization of Fermat's little theorem. And that will imply this result. So I'm going to write this claim and I'll prove the claim later. So the claim is m to the k. So if p and q are prime, let me erase this. Well, okay. Everything is within this proof, so we've assumed p and q are prime. So the claim is that m to the k p minus 1 times q minus 1 is congruent to 1 modulo pq. And if we can prove that claim, we'll be done, because this is now just going to be congruent to 1 times m mod pq by the claim as desired. So the only thing that needs to be shown now is this claim. I've isolated all the action in this claim, which looks like some kind of generalization of Fermat's little theorem. Okay, so let's prove this claim. Find the easiest proof of this claim. Okay. So okay, I'll tell you what's bugging me. What's bugging me is the proof I thought of presenting actually required K to be positive. Now, can we assume that? Let's think about it. I'm not actually sure. So ED is congruent to 1 modulo phi. Phi divides ED.
Because P is prime.
Excuse me?
P is prime, right?
P is prime, yeah.
And you can't have a negative prime. We haven't defined negative primes.
No, phi is not prime.
Oh, phi, sorry.
Yeah, phi is, remember, phi is P minus 1 times Q minus 1. Phi is definitely composite. Okay. And this is really a question about the division algorithm. So ED is some positive number. It's congruent to 1 modulo phi. So does that mean I can write it as some positive number times phi plus 1?
Well, if we said that ED is positive, then K times E would also have to be positive. And we know that phi is positive because it's a composite number multiplied, like a product of two primes. So then K would also have to be positive.
Okay, so wait, so E is not prime. D is not prime either. Okay, let's assume for now it's positive. We'll deal with this issue later, okay? And actually, I should have said, why does D have an inverse? Why does E have an inverse modulo phi? Well, because it's relatively prime to phi, right? We proved that in the previous lecture. E and phi are relatively prime, so E has an inverse. Okay, let's assume K is positive for now. Okay, so let's prove this claim. So this proof is going to have two cases. Sorry. The claim is if M is not congruent to 0, mod PQ, then this is congruent to 1. Actually, let me edit this claim. Let me just make it really handle all the cases at once. Let's prove this claim, which is also clearly enough to prove what I want. We prove that M. We'll just literally prove. Well, I mean, yeah, what the whole point of the proof is. Okay, I guess I didn't achieve much by structuring the proof this way. So there are two cases. So case one is assume M is not congruent to 0 mod PQ. Okay. So now, no, sorry. Assume M is not congruent to 0 mod P. And not congruent to 0 mod Q. Okay. Now I can apply Fermat's little theorem, right? By Fermat's little theorem, I have that M to the P minus 1 is congruent to 1 mod P, and M to the P minus 1 is congruent to 1 mod Q. Okay. Now I'm going to do something kind of sneaky. So in other words,
oh, sorry, wait. Shouldn't the last conditional be, yeah, like in the chat?
Q, sorry, m to the q minus 1. Yeah. Thank you. In other words, P divides actually no, I don't want to do it this way. Okay, so I applied Fermat's little theorem twice. Now I'm going to do I'm going to observe that this quantity that I care about, m hat, this is congruent to m to the p minus 1 raised to the k times q minus 1 times m mod p. That's just rules of exponentiation, which is congruent to 1 to the k q minus 1 times m mod p, which is congruent to m mod p. Okay. And similarly, I have that m hat is congruent. Now, if I do the exponentiation the other way, it's congruent to m to the q minus 1 raised to the k times p minus 1 mod q. I can do this just by rules of exponentiation, right? And now, what's the next step?
We can replace m to the q minus 1 with 1. Because,
yeah, by Fermat's little theorem applied to m to the q minus 1 mod q. So this is 1 to the k times p minus 1 mod q. Oh, sorry, this is all plus 1 times m. So times m mod q congruent to m mod q. Okay. Now I'm going to use the Chinese remainder theorem. So I'm going to consider the system of congruences x is congruent to m mod p and x is congruent to m mod q. So I have just produced a solution to this, right? Namely m hat. So m hat mod PQ is a solution to this system, to this star. So by the way, why is it okay to replace m hat by m hat mod PQ?
Because we know that we're trying to figure out m, and we know that m is going to be between 0 and PQ.
Right, but I'm specifically talking about this m hat over here, right? Yeah, I mean, so we're not talking about m yet. I mean, the reason is that, well, m hat is equal to some multiple. Let's not use the letter k again. Is equal to some number h PQ plus its remainder, right? And this first part is not going to affect whether or not it satisfies the congruence because it's congruent to 0 mod p and congruent to 0 mod q, right? Okay, so just a little elementary modular arithmetic there. So m hat mod pq is a solution to star. Do you know any other solution to star?
I mean, the one given by the Chinese remainder theorem.
Okay, the one given by the Chinese remainder theorem. But do you know an even simpler one? If I asked you this question like 2 lectures ago, I asked you to solve these equations.
Just m.
Just m, right? So m mod pq is also a solution to star. So now by the uniqueness part of the Chinese remainder theorem, these have to be equal. M hat is congruent to m mod pq as desired. Okay, so it's a sneaky argument. I basically said, hey, look, this particular thing that RSA produces, this m hat, it satisfies these two congruences by Fermat's little theorem. But wait a minute, that system has a unique solution, modulo pq, so it has to be the one I started with. Okay, now there's another case, which is one of these things is divisible by m. So case 2 is that either m is congruent to 0 mod p, or m is congruent to 0 mod q. This is actually much easier. I'll just skip it. You can read it in the book if you want. But really the main action is in this first case here. I really used like the whole kitchen sink, right? I used Fermat's little theorem. I used the Chinese remainder theorem. I used inverses. I used all the rules of modular arithmetic. But anyway, in the end, I proved this claim. So any questions about the proof of this? Oh, so by the way, so why was I getting annoyed about k being positive? Does anybody have a sense of why I might be bothered by that?
Yeah, oh, if k isn't positive, then m might not be an integer. Or sorry, m raised to the power of k to the everything might not be an integer.
So if k is negative, then I would have had to prove to you that the rules of exponentiation modulo prime work the same way for negative exponents. They do. I just haven't proven that to you in the class, so I didn't want to use something I didn't prove. Now, yeah, can we take k to be positive? You know, it's actually so let's see. So let's see. E times d is a number which
we can choose d to be positive, right?
We can choose d to be positive, yeah.
And then e is from a positive set.
Good, great argument. Yeah. So your argument is, well, you chose e and d to be positive. Phi is also positive, and phi is actually big, right? So if k was negative, then the right hand side would be negative. So you can choose k to be positive. Thank you. That's a good argument. Okay, but anyway, that completes the proof that this RSA works. So basically, you know, the underlying idea was that you can reverse this exponentiation by e by exponentiating by e inverse modulo phi, not modulo n. And the reason for that is that then you can apply Fermat's little theorem and get these system of congruences, which then you can analyze using the Chinese remainder theorem. So it's like an amazing proof. Like, I don't know how they came up with this. I think it's absolutely stunning, but this is literally what's going on when you send your credit card on the internet. So, okay, this won't be on the exam or anything, but it's a nice motivation, and there are some homework problems where you just do this computation. It uses pretty much everything we learned about number theory. So any questions about this?
This is overwhelming.
Yeah, so don't feel bad if this is overwhelming. Okay, so this is one of those things where, so some proofs, very few proofs, you can understand them while you're hearing them the first time. This proof, I did not understand it the first time somebody explained it to me. I had to go down and read it. So don't feel like there's something wrong if you can't follow every aspect of it. The rough idea was, the idea is that exponentiating by d, which is the inverse of e modulo phi, undoes this raising m to the e mod m. That's the rough idea. That you're somehow canceling the exponents, but you're doing it in this very specific way because Fermat's little theorem is involved. Okay, so in the remaining, yeah, this is also kind of a good example of some math that people came up with kind of just for fun, like maybe like 150, I don't know how many years ago, like hundreds of years ago. And then it ended up being like super duper useful, which is something that actually happens more often than you might think. But okay, let me now say a little bit about the exam. Okay, so the exam is 24 hours open book.
Hey, sorry, can you scroll off like 1 second?
Sure.
Okay, thank you.
Yep. It's a 24-hour open book exam that's released at 8 a.m. on Tuesday and due 8 a.m. on Wednesday, just like the quizzes. You're not allowed to collaborate.
Is it on B course or somewhere else?
It'll be on Gradescope.
Oh, okay.
There's no collaboration. And you know, you're not allowed to look things up on the internet, etc. But you do, it's an untimed exam. It's not meant to take 24 hours. It's meant to take like 1.5 hours. So, you know, it's really meant to be untimed. It's not gonna, I'm not gonna make it so you need to spend 10 hours solving the exam. So yeah, I mean, you should be able to finish it in a couple of hours, I would say. Now, what do I want to say about studying for the exam?
Are we going to
So
have
first, here's a
lecture?
quick recap of material. So they're roughly, at a high level, we achieved three different things before the midterm so far. So first, in lectures 1 through 3, we discussed how to write and interpret precise mathematical statements. So involving various logical connectives and quantifiers involving, you know, not, and, or, there exists, for all, propositional functions, conditionals, biconditionals, et cetera, et cetera, et cetera. And it's very important to understand what those mean. And an important thing here is what you should know operationally is you should know how to negate a quantified statement and how to prove a quantified statement. So what's the structure of a proof of a statement which has one of these quantifiers. And you should also know how to use a statement which has one of these quantifiers. And by use, I mean, when you assume such a statement is true, and when you know such a statement is true, what does it put on the table, which is something I keep mentioning, which is just this, metaphor for all bound variables. And statements we know are assumed to be true. So when you're reading or writing a proof, you should always be aware of what's going on the table. Okay. Now lectures 4 and 5, we learned about sets and functions and various properties of functions like one-to-one, onto, what it means to be a bijection. And then we use these to study sizes of infinite sets, namely this concept of cardinality. Now, we also did some operations with sets like subset, element, something is an element of a set, power set, et cetera, et cetera, et cetera. And this is a language that we're going to keep using throughout the course. It's also a test bed for these different proof techniques. So I guess we also learned, proof techniques. So direct proof, proof by contradiction, proof by contrapositive. And really here, I would say the things to be very careful about are, you should know how to, you should know the difference between one-to-one and onto. This is a very common point of confusion in this course. You should know how to prove either of those properties, how to disprove them. You should know how they're related to each other. This is a very common point of confusion. And another thing I would encourage you to review is a lot of people, the proof about the diagonalization proof that the irrational numbers are uncountable is really subtle. So I would advise everybody to review the diagonalization argument. And then finally, a very important thing, which I've also noticed in quizzes and homeworks, is that, be aware of the different types of objects, right? So for example, if you say something like, if you say something like a set is onto, this doesn't make sense, right? Is nonsense. So it'll help you keep everything in order, that whenever you write down a symbol, be aware of how it's quantified, be aware of its type. And then lectures, 6 through, I guess 6, 7, 8, 9. This is, okay, number theory, and I'm not going to re-review this since we did this very, very recently. Just look at the slide on the last lecture. But again, a tricky thing to be aware of is what's the difference between A mod M and A is congruent to B mod M. Also be aware that, always remember the modulus when you're doing modular arithmetic. Yeah, okay. I guess I don't have much more to add. Maybe just review the big picture at the end of lecture 8. And I just want to say lecture 9 is not on the midterm. What we did today is not on the exam. The exam is only stuff until the previous lecture. Now, if you, in terms of recapping the material, the thing I would really advise you to do So you don't need to know everything on the, in the book, right? So you don't need to know everything in the book. Instead, you want to focus on what's in the notes, on the lecture notes, and what's covered in the homework and quizzes. But there are these end of chapter summaries. If I don't know if anybody has, maybe many of you have already been looking at them. So at the end of every chapter, there's something that says key terms and results. So these are like ready-made, like, you know, cheat sheet for the chapters. It's like a very concise index of all the definitions in that chapter. And I encourage you to review those when you make your own notes. So key terms and results. Is useful. And you can use that to, because the book is very verbose. It can be a little overwhelming, but these are really good. So this is what I want to say about the material. And finally, I want to remind you of how do you solve a prove or disprove question, right? So prove or disprove, you know, some proposition. Many of you have asked have asked about this because it's really a lot more open-ended than the previous math courses you've done. And I would say here are the steps. One is determine the precise meaning of the proposition by writing down all the relevant definitions. Okay, definitions are your entry point into the mathematical world. Without the definitions, you can't even know the meaning of what you're trying to prove. Then write the statement and its negation. Write the statement and its negation. Write them down formally. So this will show you what the quantifiers are in each case. And this is why it's important to know how to negate, right? So you're given the proposition, you don't know if it's true or false. Well, you better clearly at least know what it means for it to be true or what it means for it to be false. So write down this proposition and its negation formally. And then you have to form a belief about whether it's true or false. So maybe try a few small examples to form a tentative belief. In either the proposition or its negation. And then step 4 is to use the proof techniques. To prove or disprove the proposition. Now, you know, use the proof techniques, you know, and a bunch of other stuff, right? And the definitions, and you know, whatever the hypotheses are. I mean, okay, the proof techniques are a structure of the proof, but keep in mind the definitions, hypotheses, plus whatever known theorems to prove or disprove the proposition. And in general, a good rule of thumb is choose the proof techniques that put the most things on the table. They give you the most to work with, right? So choose techniques that put a lot on the table. And this is not always going to work. If it doesn't work, articulate what you learned and repeat. Right? So if didn't work, go back to step 2. Okay? And don't panic if you can't solve a problem right away. Okay, so the last thing I want to say is watch the B courses video on writing. In case you haven't already. writing is very important in this course. In order to get full credit, proofs will have to be clearly written. So please watch that video. And I'll send some more maybe tips via email. But anyway, that's it. So good luck.
Is there going to be a lecture on Tuesday?
No, there's no lecture on Tuesday.
Okay, thanks.
Will there be discussion on Monday?
Yeah, there'll be discussion on Monday.
Oh, and also, like obvious question, there won't be a quiz next week.
There won't be a quiz on Tuesday. Oh yeah, I have a long office hour tomorrow in person also, in case anybody wants to come to that. But yeah.